In lesson 61, it will be broken into a few parts. First, you're going to carry out investigations from your textbook, and then you will see solutions to those investigations before we move on to looking at a few more examples around kinematics. Let's take a look at the chart below. We have definitions for position, velocity, and acceleration. We usually denote position as s as a function of time s of t, velocity as v, and it is defined as the instantaneous rate of change of position. Therefore, v of t can be looked as the rate of change of s of t, and in calculus we know this means s prime of t, the first derivative. Meanwhile, acceleration a is defined as the instantaneous rate of change of velocity. As a result, a of t is v prime of t, or the second derivative s double prime of position. Notice that there is a slight difference when we talk about distance versus displacement. So for distance, it's referring to the total path length. So if I'm going around the track 5 times, I have to multiply the distance around the track by 5. However, if I start and finish on the same spot on the track, then the change in position, or the displacement, is 0. Now let's move on to your investigation. Pause the video until you have finished at least the first one before you look at the answers. Now let's take a look at investigation 25. You're given a function of Ben's position, s of t. Use your GDC to plot the graph of Ben's displacement against t, and then you're asked to find Ben's velocity. Let me get a set of axes out. Okay, well, this is thick. It's okay. When you plot your graphs on a graphing calculator, you should see that the position, it's something like this. It crosses the x-axis at 2 and 4, I believe. And it starts at -2. And then for the velocity function, which you will find through taking the first derivative of s of t, let's see, 3t squared minus 12t plus 9. Then you end up with a 0 here and a 0 here, and also the vertex of this quadratic function for velocity occurs at 2 and -3. So obviously my graph is not drawn to scale, but you get the idea. So the red one is v of t, let's label them, and the blue one is s of t. Okay. What do we notice? Write down the time intervals when the velocity is positive. So velocity is positive at time 0 to 1, as well as 3 to 4. And v of t is negative when time is between 1 and 3 seconds. Okay, let me label those points on the graph as well. Okay. Which direction is Ben moving in each time? When it has positive velocity, he is moving towards point B, i.e. the positive direction. And when velocity is negative, he's moving towards point A in the negative direction. That means the sign of velocity actually represents the direction. Oopsies. Let's try this again. the direction that he's moving towards. And what is the connection between speed and velocity? Now, speed is a scalar quantity, meaning that speed doesn't have any direction, but velocity does. Okay, so now we can say that speed, we're going to use a fancy word, is the magnitude of velocity. So magnitude is a word that we use to refer to the size, okay, size only. But it shows no direction. Later on in chapter 9, when you learn about vectors, then we're going to distinguish between scalar and vector quantities in more details. Or for those of you who take physics, you know what I'm talking about. Number 5, find the times at which his velocity is 0. What is he doing? Well, the time that velocity was 0 was 1 and 3 seconds. And you'll notice on the graph, let me go back to the graph, that at these points, he is actually going from a positive direction to a negative direction, right? When the sign of velocity of v of t changes. So we say that he's actually changing direction. Okay, or he's turning around. Number 6, at which 2 times did Ben's maximum velocity occur? Describe his motion at these times. While his max velocity occurs at time equals 0 and time equals to 4 when he was moving at 9 meters per second, and he was passing or passes A for the first time. And then the next time, which is at 4 seconds, he was passing point B for the first time. Okay, I'm gonna wrap. So this is your very first investigation in this lesson. Did you try investigation 26 yet? If you haven't, pause the video now. If you have, let's continue. Here we're going to look for the velocity acceleration function based on the given position function s of t. From the chart, by definition, velocity is the rate of change of position over time. Therefore, we have 3t squared minus 7 times 2, 14t plus 11. This is the velocity function. Acceleration function is the derivative of velocity function. So let me write this down, which is 6t minus 14. You're interested to find in number 2, the times which the particle is at rest, the particle is speeding up, and the particle is slowing down. A quick way to visualize this is actually to think about the graph of v of t times here. You can use your graphing calculator to do this, which saves some time, or you should have done this already. So the first 0 occurs at 1, the second 0 occurs at 3.67, and the vertex is at around 2.33 seconds, halfway between the 2 zeros. We notice that, let me write this, v of t is equal to 0 when the particle is at rest, occurs at t equals to 1 second and 3.67 seconds. How can we tell if the particle is speeding up or slowing down? From the last investigation, we say that speed is the magnitude or the absolute value of velocity. You can also use a benchmark where if velocity is 0, what does that mean? That means that the object has stopped. As a result, the further away you are from 0, the faster the object is moving. It's just in different directions. Okay. And it's getting faster and faster and faster, slower and slower and slower. So let's see. When we are from 0 to 1, we're coming towards, the graph is coming towards the time axis. That means it's slowing down. Between 1 to the vertex, it's going away from the axis. So this is a speed up. So using the same logic, it's speeding up in this portion as well. But we can mark down these time intervals, or time is greater than 3.67. What you can also know, you may also notice, is that if you have also graphed your acceleration function, you will notice that when the object is speeding up, the velocity could be negative, but what must be true is that the acceleration is also negative. If you have not make this graph for acceleration, you can also tell by considering the slope, or the gradient, I shouldn't use the word slope, the gradient of the graph during this time. If I draw tangents anywhere in this interval, these tangents have a negative slope, which is the same as the sign of the velocity. So that means we have speeding up. If I draw tangents along this section, the tangents are all positive gradients, which matches with the sign of velocity. So we can say that here v of t and a of t have the same sign. Now 2C asks us to state when the particle is slowing down. Well, obviously, it must be the opposite, right? So it must be any time from 0 to 1, or any time between 2.33 seconds to 3.67. And in this case, when velocity is positive in this region, the slope of those great tangents for acceleration are negative. Here, when velocities are negative, acceleration is positive. And we can say that v of t and a of t have opposite signs. Eek. And these observations help us answer number 3, what must be true about the signs of velocity. So we have included all the answers there. And number 4 asks, at what values of t does the particle change direction? How can you tell this from the graph of velocity against time? I'm going to change the question to velocity against time. And really, these are the zeros, right? You may notice that's when v of t is 0, it indicates that there is a change in direction at t equals 1 and t equals to 3.67 seconds. This completes the first part of this lesson. In the next video, we're going to do a few different examples applying these ideas that we have just learned.